Large language models process prompts as a single, unified stream of text. Unlike traditional software, the user's input and the developer's system instructions share the exact same input channel. Because the model reads everything as one continuous block, an attacker can insert a malformed text sequence. This is known as an instruction override, a technique where user data is formatted to trick the model into abandoning its original directives and executing the attacker's input as a system command. This diagram illustrates a standard user-to-LLM API pipeline. Watch what happens when a malicious prompt enters the stream. The user input, shown in red, collides with the system's baseline instructions, functionally erasing the safety guardrails before the data ever reaches the LLM node. In standard software architecture, a database query keeps logic and user data strictly separated. Natural language processing lacks this boundary. The text is the code. Since the LLM itself cannot natively distinguish between a benign user request and a malicious system command, we cannot rely on the model to police itself. An external zero-trust defense architecture is mandatory before the prompt even touches the primary model. Early attempts to secure models relied on single-layer defenses, like wrapping the prompt in restrictive instructions or using simple regular expressions. Regular expressions, or regex, are sequences of characters that specify a search pattern in text, but attackers quickly learn to bypass these static filters using encoding tricks or complex role-playing scenarios. A static defense is rigid. When faced with the adaptable, highly fluid nature of human language, that single barrier inevitably shatters under pressure. This introduces a severe engineering constraint, the latency paradox. If you add enough complex semantic filters to catch sophisticated attacks, the processing time spikes, crippling the application's response speed. Securing an LLM requires a heterogeneous defense-in-depth pipeline. Instead of one massive filter, the system stages different types of validation, ranging from lightweight math to heavy machine learning, in a specific sequential order. The framework we are analyzing today achieves a 98.9% injection detection accuracy while maintaining an average latency overhead of less than 150 milliseconds. Successfully deploying enterprise LLMs requires balancing the need for heavy, nuanced semantic analysis with the requirement for high-speed processing through intelligent architectural staging. The pipeline begins with Stage 1 input sanitization. The goal here is to strip away cheap structural attacks instantly before invoking any computationally expensive machine learning models. This flowchart represents our baseline architecture. All user input first routes through the Stage 1 sanitization block before it can proceed toward the LLM. This stage targets structural vulnerabilities, like the homoglyph bypass. Malicious actors substitute standard Latin letters with visually identical Unicode characters, like Cyrillic, to slip past keyword blacklists unseen. Stage 1 intercepts the string, runs encoding normalization, and converts deceptive Unicode back into standard text, where it can be blocked. Alongside normalization, this layer applies fast, deterministic mechanisms. It scans for known injection signatures using strict regex pattern recognition and filters the output against a hard-coded blacklist of dangerous phrases. It also performs entropy analysis. Entropy, in this context, refers to the measure of randomness or unpredictability in a string of text. Attackers often submit statistically abnormal, low-entropy input strings, like repeating a single character hundreds of times, to overwhelm and confuse the model's tokenizer. By applying these fast, deterministic rules, Stage 1 acts as a highly efficient primary shield. It drops badly formatted requests early, preserving computational power for complex threats requiring deeper analysis. Deterministic rules are excellent at evaluating syntax, but they have a critical blind spot. They cannot understand semantic intent. Look at the updated flowchart. We bridge this semantic gap by inserting a Stage 2 constitutional AI block squarely between the sanitization layer and the primary LLM. This layer is designed to catch manipulative strategies like role switching. Role switching tricks the LLM into adopting a persona to ignore safety protocols. Since it lacks banned keywords, it sails through Stage 1's filters, but is instantly intercepted and flagged upon entering Stage 2. Stage 2 neutralizes these exploits using constitutional AI. It is a method of machine learning evaluation where models are guided by a specific, written set of principles rather than human feedback alone. A secondary, independent AI agent reviews the sanitized prompt. It scores the user's intent against a strict set of weighted ethical principles, specifically allocating 40. Stage 2 transitions the defense from simple syntax checking to true intent evaluation, ensuring that the primary LLM is insulated from manipulative logic. Even with robust input filtering, we have to account for the final fail-safe scenario. What happens if the primary LLM simply hallucinates, or a novel zero-day jailbreak manages to bypass the first two stages? This diagram shows the completed pipeline. We add a Stage 3 output validation block, positioning it after the primary LLM node, but right before the final response is delivered to the user. The core mechanism of Stage 3 is a machine learning classifier called toxic-bert, which scans the generated response for harmful content. It runs alongside a cross-site scripting, or XSS, format validator. XSS is a vulnerability where malicious scripts are injected into trusted applications, and this validator ensures the LLM hasn't accidentally leaked internal system markers into the final text. The toxic-bert model acts as a rigorous final checkpoint, achieving a 98% accuracy rate in catching and blocking malicious outputs. This brings us back to the core engineering tension. Running regular expressions, a secondary AI evaluation agent, and a deep learning classifier takes processing power. The challenge is executing all of these requests in under 200 milliseconds. This waterfall chart maps the execution lifecycle. When Stage 1 catches an attack, it drops the request at 45 milliseconds, preventing heavier ML models from spinning up. For full validation, GPU acceleration drops toxic-bert inference from 200 to a tight 50 to 80 millisecond window. Intelligent architectural staging solves the latency paradox. You can deploy heavy machine learning security provided you use fast filters up front to dramatically reduce the volume of data requiring deep evaluation. A perfect logic pipeline is practically useless if the underlying infrastructure can be easily compromised. To prevent this, the entire framework is encapsulated in a production-ready Docker deployment. It enforces non-root execution, running strictly under a restricted user ID, and utilizes read-only file systems. This hardens the container and completely prevents privilege escalation attacks at the operating system level. This data table shows the architecture's performance against over 1,000 adversarial attempts. It maintains a 98.9% detection accuracy and 145 millisecond average latency. Looking closely, the pipeline successfully detected 100% of instruction overrides and 99.2% of complex jailbreak prompts. From an operational standpoint, the most vital metric is the 0.4% false positive rate. This ensures that the heavy security apparatus does not falsely block legitimate queries and degrade the actual user experience. This architecture establishes a modular hierarchy where specialized AI agents are deployed specifically to police the primary model's logic. As attack vectors continuously evolve beyond static, predictable rules, bolting on simple filters is no longer sufficient. A modular, deeply integrated architecture is now the mandatory baseline for deploying any large language model into a production environment safely.